In this video, we are going to talk about the null space and also introduce the idea for range. This is our overview slide, which we'll spend about 5 minutes going over before we go over these topics in more detail and with more examples. First, we're going to review some things about functions. So the first important thing about functions is that they are well defined. So if we have a function that maps from A to B, every element of A then is mapped to exactly one element of B. We also have one-to-one, sometimes called injective functions, where every element of B is mapped to from at most one element of A. And then we have onto and surjective functions. For every element of B that is in the set B, there exists an element A in the set A such that f of A is equal to B. First, we define the null space, also known as the kernel, for T, a linear map from V to W. So the null space of T, denoted null T, is the subset of V consisting of those vectors that T maps to 0. So in other words, the null of T is equal to the vectors V in our set V. That's where T is mapping from. It's the elements V such that TV is equal to the 0 vector. We have this first example where T maps from F3 to, oh, this shouldn't be R, this should be F. I'm really used to thinking of real numbers or R3, but this is F3 mapping to F. Your book puts F to emphasize the fact that everything we talk about also applies to complex numbers. Anyway, so we have our function T that maps from F3 to F. So it takes this three-dimensional vector, Z1, Z2, Z3, and it maps it to the single scalar Z1 plus 2Z2 plus 3Z3. We want to find a basis for the null space. So first we look at our mapping. So T takes our Z1, Z2, Z3 vector, maps it to a single scalar, Z1 plus 2Z2 plus 3Z3. If we set this equal to 0, that gives us the condition that Z1 must equal to minus 2Z2 minus 3Z3. So in other words, our null space, the vectors that get mapped to 0, are the ones where the first coordinate, Z1, is equal to minus 2Z2 minus 3Z3, and then Z2 is any arbitrary number, and Z3 is any arbitrary number. We can then do the work to separate out our Z2 and Z3 components to get a basis for negative 2, 1, 0 and negative 3, 0, 1. It's really important that you remember that the null space, they're vectors from V that get mapped to 0. Because later we'll talk about range and, a few chapters later, you're likely to forget that. But if you forget where the null space comes from, that it comes from V, you literally don't know what vector space you're in. It's like there's no faster way to say I'm literally lost. I don't even know what space I'm in. So remember, the null space are vectors from V. And in particular, we have this theorem that the null space is a subspace. So suppose T is a linear transform from V to W, the null of T is a subspace of V. Next, we come back to this one-to-one injective idea, and we say that T going from V to W is called injective if TU equals TV implies that U equals V. And if U does not equal to V, then TU should not equal to T of V. Which brings us to this other important theorem that gives us a little bit of an indication of why the null space is so important, and that is injectivity is equal to the null space equaling 0. So let T be a linear map from V to W, then T is injective if and only if the null of T is equal to 0. And remember, once you're injective or one-to-one, you're halfway to being a homomorphism. The other half is the onto surjective. Last, we're going to introduce the concept of range and introduce the fundamental theorem of linear maps. These two topics are the main topic of our next video. So the range for a function T from V to W, the range of T is the subset of W now, consisting of those vectors that are of the form T of V for some vector V in V. So in other words, in algebra, you used to think of domain and codomain, and then range would be the values in the codomain that actually had something mapped to them. So this is totally consistent with that idea. The range of T is equal to TV for some V in our starting vector space V. And we have this example. Find the range and a basis for the range of T going from R2 to R3. And we have this linear map T of xy. So again, xy, we're in R2. And we come out to R3, and R3 vector after the transformation is 2x, 5y, and x plus y. So in other words, T of xy equals 2x, 5y, x plus y, which this here is exactly our range. This is the form of the vectors that T will map R2 onto. And we have this theorem that the range is also a subspace. So if T is a linear map from V to W, then the range of T is a subspace of W. And again, now it's important to remember range of T is a subset of W. The null space of T is a subset of V. And then we have the fundamental theorem of linear maps. Suppose V is finite dimensional and T is in the set of linear maps from V to W. Then the range of T is finite dimensional and the dimension of V is equal to the dimension of the null space of T plus the dimension of the range of T. And finally, I have this note that I kind of tell you, I feel like it's important that null of T is a subspace of V and range of T is a subspace of W. So that concludes our overview. So we'll go back and take a closer look at these functions and null spaces. The first note for functions is that they are well defined. So we have F mapping from a set A to a set B. So every element of A needs to map to exactly one element of B. So an example of something that is not a function, I have this drawn here. It's not a function for two reasons. This element of A is mapped to two elements of B. So it's mapped to too many. And this comes up, in, I guess, what do I want to say, real life? If you look at the square root of 4, that can map to -2. It can also map to +2. So square root of 4 is not a function. Often, to make it a function, we'll just say we're only considering the positive square roots. And then you fix that problem. But here in this picture, we have this element of A is problematic, and it will make our function not a function. The second reason this is not a function is we have this element of A that is not mapped to anything in B. So it's not related. It just doesn't have any assignment. And so that is another example of a mapping that is not a function. Next, we have one-to-one functions. Your book likes to call these injective functions. So every element of B is mapped to from at most one element of A. So over here, we have an example of something that is one-to-one because everything in B is mapped to at most by one element of A. It's okay that it's not mapped to any, just that you don't want something that's mapped like over here. No, like over where? Here. It's not one-to-one where this element of B has two elements of A mapped to it. And this also is not one-to-one, specifically the two elements of A mapped to a single element of B. And then last we have onto or surjective functions. For every element in B that is in the set B, there exists an element A in the set A such that f of A is equal to B. Here, this function is not onto because there's an element B that doesn't have anything in A mapped to it. This function is onto because all three elements of B, there's only three elements of B, has something in A mapped to it. But again, it's not one-to-one because B has two elements from A. This element of B has two elements of A mapped to it. Here we have something that is also onto. I have drawn 4 elements of B, and presumably those are all the elements in B, and they all have something from A mapped to it. And this is one-to-one and onto. Here, this function is not onto because I have this element in B that has nothing mapped to it. And I need something in A to map to it. Here, this isn't even a function at all, but it does map onto B. Now that we've talked about functions in general, it's going to come up again later, but we're going to go on for now and talk about the null space or the kernel of a transformation, T. So if T is a linear map from a vector space V to a vector space W, the null space of T, denoted null T, is the subset of V consisting of those vectors that T maps to 0. So null of T is equal to the elements V in the set V such that T of V gets mapped to 0. Our first example of a null space, if we have the function T of V that maps everything to 0, so every element V, every vector in the vector space gets mapped to 0, then the null of T is equal to every vector in V, or the whole space V. And this is a pretty extreme function, T, when the null space is equal to V. And if you imagine it, think of, a vector space, a three-dimensional vector space. And if T maps, let's say T maps from R3 to R3, but what it does is if T takes this whole entire vector space of R3 and maps it to the 0 vector, it's sort of crushing down a whole three-dimensional space to a single point. It's like a black hole transformation. So this is a pretty extreme transformation, and you know that just by looking at the null space or the kernel. The other flip side of a transformation that's polite, I'm going to call it a polite transformation that doesn't just crush everything down to a single point. A very polite transformation will map the 0 vector to the 0 vector. It just kind of very gently says, oh, you're 0, why don't I put you to 0? Doesn't that seem very polite? In contrast, this is like a black hole that just crushes everything. So that's kind of my diatribe to tell you how the null space or the kernel can tell you a lot about a transformation. Our next example, we saw it in our overview, but we'll go through it in more detail here. We have the transformation that takes z1, z2, z3 to a single scalar, z1 plus 2z2 plus 3z3. We want to find a basis for the null space. And I'm just going to write this in kind of this column vector form. So T is going from F3 to F. T takes our z1, z2, z3 to a single scalar, z1 plus 2z2 plus 3z3. Because I want to find the null space, I want to know which of these, z1 plus 2z2 plus 3z3, gets sent to the 0 vector. So I set this equal to 0, and I find that the F3 vectors that get sent to 0 are the ones where z1 is equal to negative 2z2 minus 3z3. So our null space, our null of T, is equal to z1, our first coordinate is minus 2z2 minus 3z3, and then z2 and z3, they're free. So there's an infinite number of vectors that map to 0, an infinite number of vectors in the null of T, because there's an infinite number of possibilities for z2 and an infinite number of possibilities for z3. But I'm going to rewrite this so I can find my bases. I'm going to rewrite this to explicitly show z2 and z3 at each coordinate. So the top coordinate I'm going to leave as minus 2z2 minus 3z3. On the second coordinate, I want to show that there is a z3, it's just multiplied by 0. So I'm going to have 1 z2 plus 0 z3, and over here I'm going to have 0 z2 plus 1 z3. And I do that because I want to break this down into a scalar z2 times a vector plus a scalar z3 times a vector. So you can see how I factor out my z2 over on these coordinates, so I get a minus 2, 1, 0, z2, and over here for my z3 terms, I'm going to have my z3, factor out my z3, and I get a minus 3, 0, 1 vector. And what this tells me is my null space then is spanned by the vectors negative 2, 1, 0, and negative 3, 0, 1. And since these vectors are not scalar multiples of each other, they're also linearly independent, which means negative 2, 1, 0, and negative 3, 0, 1 is a basis for the null of T. Our next example, suppose D is the linear map from the polynomial space to the polynomial space, that is the differential map defined by d of a polynomial is equal to the polynomial prime, or the derivative of the polynomial. Find the null space of d. And I just want to write this out. So d is a mapping from the polynomial space to the polynomial space over real numbers. In other words, our coefficients are going to be real numbers. And our linear map D takes a polynomial p of x, and it gives us p prime of x. And now I'm interested in finding the null space, so I'm going to set this equal to 0. I want to know the polynomials such that the derivative of the polynomial is equal to 0. And it is the constant polynomials whose derivatives equal 0. So the polynomial with first derivative equal to 0 are the constant functions, and therefore the null space of D is equal to the set of constant functions. Our next example, suppose T is the linear map from the space of polynomials to the space of polynomials. Define that by T of the polynomial of x is equal to x squared times the polynomial. Find the null space of T. So I want to first start by writing this out, that T maps from the polynomial space to the polynomial space. T on our polynomial of x is equal to x squared times our polynomial. Since I'm looking for the null space, I'm going to set this equal to 0. Now x squared, that can be any real number. So if I want this to equal to 0, this x squared times p of x to equal to 0, we need to have our polynomial equal to 0. There's nothing else that will work for all real numbers x, which means the null space of T is equal to the 0 polynomial. Our last example for now is suppose T goes from f infinity to f infinity. Remember, these are just an infinite sequence of numbers. It's like, you know how you have R2, R3, it's like R infinity. And now we can also have complex numbers, f infinity. And our transformation is going to be the backward shift on this infinitely long vector. So T of x1, x2, x3, dot, 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 is equal to, we just get rid of this first term. So it's x2, x3, dot, dot, dot. We want to find the null space of T. So now looking at my transformation of x1, x2, x3, right? x2, x3, all of this is going to equal the 0 vector only if x2, x3, and all the other coordinates is equal to 0. So what we get is the null space of T are vectors of this form, where the first coordinate can be anything, and then all the other coordinates must be 0. Next, we're going to look at this important theorem that says the null space is a subspace. So suppose T is a linear transformation from V to W, then the null of T is a subspace of V. We are going to do the proof of this, and I'm going to just start by writing T is one of the linear operators from V to W. And it's important that you realize we're talking about linear transformations here. And linear transformations, that includes anything that can be represented with a matrix. And we have T mapping from set V to set W. To prove a subset of a vector space is a subspace, we have 3 conditions we need to be able to show. And again, this is from our video on subspaces. So the 3 conditions are, we need to show the additive identity is in our subspace, and that addition is closed in our subspace, and also scalar multiplication is closed. And we're going to start with the additive identity is in the null space. But we have this theorem from our video about linear maps that says linear maps take the 0 vector to 0. So since T is linear, T of 0 is equal to 0, which means that our 0 vector is in the null space. And therefore, our additive identity 0 is in the null of T. Next, we're going to show addition is closed. So we're going to take representative vectors u and v from the null space of T. And that means that T of u is equal to 0 and T of v is equal to 0. To show closure, then, we need to consider T of u plus v. Because T is a linear map and additivity of linear maps, T of u plus v is equal to T of u plus T of v, but we also know T of u is equal to 0 and T of v is equal to 0 because they're in the null space. So the 0 vector plus the 0 vector is equal to the 0 vector, and therefore T of u plus v is in the null space of T, and addition is closed. Next, we're going to show that scalar multiplication is closed. It actually follows a lot of the same structure as showing addition is closed. First, we need to start with u is in the null space of T, and we're going to consider alpha of u. But we know by homogeneity of linear maps that T of alpha of u, we can pull out the alpha and get alpha T of u. But also we know T of u, since it's in the null space, is equal to 0. So we have alpha times 0, which is equal to 0, which implies that T of alpha of u is in the null space of T, which means that scalar multiplication is closed. And we have met our three conditions: additive identity, addition is closed, scalar multiplication is closed, to show that the null of T is a subspace of V. And I'm going to urge you again not to get lost. You want to remember that the null space, those are vectors from the space V that gets mapped to the 0 vector in W. So again, the null of T then is a subspace of V. So when you talk about the null space, you're talking about vectors in V. Next, I copied a bunch of notes so we could talk about this theorem. First, the definition of the null space is here. So the null is a subset of V consisting of those vectors that T maps to 0. We have the theorem we just proved: the null space is a subspace. We have our definition of a one-to-one function where every element of B is mapped to from at most one element of A. So it's okay to be mapped, that nothing maps to it, but it has at most one element mapped to it. Unlike here, where it has two elements mapped to it, so it's not one-to-one. So our theorem is injectivity, that's one-to-one, is equivalent to the null space equaling 0. So let T be a linear map V to W, then T is injective, or one-to-one, if and only if the null of T is equal to the 0. We are going to prove this theorem, and to prove this theorem, because of this if and only if, we have two directions to prove. The forward direction is we assume that T is injective and show that that means that the null of T is equal to 0. That's this forward direction. The backwards direction, or the other direction, is assuming null of T is equal to 0. We show that T will be injective. So null of T is equal to 0 implies T is injective. Two parts to the proof. Starting with the forward direction, if we want to show, or we're going to assume T is injective, and we want to show the null of T is equal to the 0 vector. So the thing about this is we have two sets, and from set theory, we have learned that to prove two sets are equal, that is, if we say set A is equal to set B, we want to show that A is a subset of B and B is a subset of A. So starting then with the 0 is a subset of the null of T. Well, since T is linear, T of 0 gets mapped to 0. We have that theorem from our video about linear maps that 0 always gets mapped to 0. So this means that our 0 is in the null of T. And now to show the null of T is a subset of 0, let's suppose V is in the null of T. That is, T of V is equal to 0, which, as we have seen, is equal to T of 0. So what we have right now is T of V gets mapped to the 0 vector, but we also have over here that the 0 vector, that's the 0 vector in the V vector space, gets mapped to 0. So these two vectors get mapped to 0. But we also have that T is injective, or one-to-one, which must mean that V is equal to the 0 vector. So in other words, any vector in the null of T is equal to 0. So, or the null of T is a subset of the 0 vector, and therefore T is equal to the 0. For the opposite direction, we start with the null of T is equal to 0. We want to show that T is injective, and we have these notes here about injective. So if T of U equals T of V, that implies U equals V. And if U does not equal to V, then we expect T of U not to equal to T of V. So let's see how we're going to use that. We'll start with this statement here. If T of U equals T of V, so we're going to copy it down here. Then we know that the 0 vector is equal to t of u minus t of v. It's just subtracting t of v from both sides of the equation. And because t is a linear transformation, by additivity, that means this is equal to t of u minus v. This implies that u minus v is in the null space of t, or u minus v is equal to 0, which means u is equal to v, and therefore we have shown that t is injective. To see where we are using our overview slide, we've covered all of our things for the null space. So the next thing to do is just to introduce the idea of range and also the fundamental theorem of linear maps. The range of a function t from v to w is the subset w consisting of those vectors that are of the form t of v for some vector v in the vector space v. So the range of t is equal to the vectors t of v for some v in the vector space v. We have an example, which is to find the range and a basis for the range of the transformation from R2 to R3, where we have t as a linear map, t of xy. Again, our domain is R2, and our range then is R3, which is 2x, 5y, and x plus y. Sometimes I like to write this out. T then is a set of linear maps from R3 to R2. So just to look at it in vector form, t of xy is equal to 2x, 5y, x plus y. So this here is exactly the range. It's kind of strange it asks for the range, but this is exactly it. This is what the vectors t of xy look like. We can find a basis then by separating out our x and y's, or first I did this intermediary step of writing this so that each coordinate specifies the x and y component. So the first coordinate has 2x and it has 0y. The second coordinate has 0x and a 5y. And finally we have an x and a y. So if I separate out x as a scalar and y as our scalar, our two vectors then are 2, 0, 1. And for y, we have 0, 5, 1. Which means the 2, 0, 1 and 0, 5, 1 spans our space of the range of t. So 2, 0, 1 and 0, 5, 1, they're also linearly independent because they're not scalar multiples, so they form a basis for the range of t. This manner of going from our a general vector then in terms of variables x and y over to a basis, this is the same technique we used when we found a basis for the null space. So this technique is very useful. It's one you want to remember. We have the theorem that the range is a subspace. So if T is a linear map from V to W, then the range of T is a subspace of W. And again, be careful that you don't get lost. Remember, if T is a function from V to W, the range over here are the elements that get mapped from some element in V by T over to W. So in this case, this one point is not in the range, but these 3 points are. Our final theorem that we will introduce is the fundamental theorem of linear maps that says suppose V is finite dimensional and T is in the space of maps from V to W, linear maps from V to W. Then the range of T is finite dimensional and dimension of V is equal to dimension of null of T plus dimension of the range of T. I have the theorem copied over here for your reference, as well as the definition of null space and range for your reference. So we're looking at T, a linear map from V to W, T maps from V to W. So the theorem says the dimension of V is equal to dimension of the null of T. And remember, the null of T is a subspace of V plus the dimension of the range of T. And remember, the range of T is a subspace of W. These two topics of the range and fundamental theorem of linear maps is covered in more detail in our next video. To review what we have covered in this video, we talked about null spaces, and we started by talking about functions. We said that functions were well defined, and what we mean by that is if we have a function f mapping from A to B, every element of A is mapped to exactly one element of B. We talked about one-to-one, also known as injective functions, where every element of B is mapped from at most one element of A. We talked about onto, also known as surjective functions, where for every element B that is in the set B, there exists an element A in the set A such that f of A equals B. Then we discussed the null space, or the kernel of a transformation T. So if T is a linear map from V to W, the null space of T, denoted null T, is the subset of V consisting of those vectors that T maps to the zero vector in W. So the null of T is equal to V such that T of V is equal to 0. We have this example where T goes from F3 to F, so T of Z1, Z2, Z3 is equal to Z1 plus 2Z2 plus 3Z3. So what that looks like, if T goes from F3 to F, I have T of Z1, Z2, Z3 is mapped to the scalar Z1 plus Z2 plus Z3. If we want to know where the null space is, we set this scalar then equal to 0, and we get the fact that Z1 then must equal to minus 2Z2 minus 3Z3. So the null of T is equal to the vector in F3 such that the first coordinate is minus 2Z2 minus 3Z3, the second coordinate is Z2, and the third coordinate is Z3. We have this theorem that says the null space is a subspace. So suppose T is a linear transform from V to W, then the null of T is a subspace of V. We also went back and looked at injective or one-to-one functions, and we have this note that a linear transformation is injective, then T of U equals T of V implies U equals V, and we use that to prove this theorem that injectivity is equivalent to the null space equaling the zero vector. Let T be a linear map V to W, then T is injective if and only if the null of T is equal to the zero vector. We introduced the topic of range, so for a function T from V to W, the range of T is the subset of W consisting of those vectors that have the form T of V for some vector V in the vector space V. So the range of T is equal to TV, where V comes from the vector space V. And we also introduced the fundamental theorem of linear maps, which says suppose V is a finite dimensional space and T is in the space of linear maps from V to W, then the range of T is finite dimensional and the dimension of V is equal to dimension null of T plus dimension range of T. These two topics are topics that we'll cover in more detail in our next video. But that's it for this video. Thank you for watching.